In this project, we will study effective skull modeling for forensic and medical craniofacial reconstruction. We are developing an efficient and reliable digital platform to facilitate anthropologists in placing tissues or muscles on the skull to reconstruct the facial geometry. For example, here is a set of skull fragments. They are eroded, damaged, and probably have several parts missing. Our assembly algorithm starts from such a data input. We will illustrate our skull completion pipeline first. Our framework mainly consists two steps, assembly and completion. The scanned skull fragments are provided as input data. We extract shape descriptor and match these fragments with a template skull and get initial assembly. We analyze the break curves of adjacent fragments and use their matching to refine the assembly. By this, we can get a better resembled skull. The assembled skull is usually still incomplete. Missing regions, gaps, or self-intersections could exist. We further perform a completion algorithm to repair the skull. It takes into account the intrinsic symmetry property of the skull, and when necessary, transplants parts from the template skull. And here's the final completion result. The first step of the fragment assembling is based on the matching between the fragments and the template. We first extract features on skulls and use them to provide the coarse correspondence. Our feature comparison is based on the spin image. The matched features will then guide an ICP like rigid registration for matching the fragments and the template. Here is an example of the assembled result. This assembly needs further refinement. The gaps and intersections between adjacent patches are caused by potential misalignment. On the other hand, this initial assembly reveals the adjacency relationship between fragments and provides a good initial guess for us to perform effective break curve matching in the next assembly refinement step. In this step, we refine the rough assembly result based on the geometry of the subject skull itself by analyzing break curves of the fragments. Break curves are defined as the locations along which the skull surface breaks. We consistently sample the same number of points on break curves. Given an anchor point V0, we sequentially and uniformly sample the break curve near V0 by intersecting several concentric spheres circled at V0. Then we can approximate the least square transformation error between two break curves and glue the best matched fragments. Here is an example of the assembled result after the refinement using break curves. The assembled skull is still usually incomplete. It can still have missing regions, gaps, or self-intersections between reassembled fragments. We develop reliable symmetry detection and completion algorithms for these damaged regions. If damages exist on both sides with respect to the symmetric plane, a template-based repair is performed to ensure the robust completion. The inherent symmetry of skulls can provide an accurate and natural repair on damaged regions, preserving geometric subtlety of the repaired skull. Despite its accuracy, symmetry-based completion cannot handle skulls whose both sides with respect to the symmetric plane are missing. On a skull damaged like this, the template shall be used to fill the hole. We compute a non-rigid registration between the subject and the template skulls. With the mapping, corresponding regions on the template are deformed and transplanted onto the subject skull. These transplanted regions are finally refined using a biharmonic function. After this refinement, a more natural patching will be obtained. Here we show our final completion result.